So for the remaining questions, we're going to start worrying about isomers. So two compounds below have the same molecular formula, which can be EZ isomers, and name the isomers. Well, if we look at A, it is 2-methyl propene. There's carbon 1, carbon 2 with a methyl, carbon 3. And then B is 1, 2, 3, 4, bute. Double bond starts at carbon 2, so bute-2-ene. Now, the way that you can tell whether or not EZ isomers can exist is that they only exist when you have two different things on each carbon. Now, compound A is carbon here, which is of course carbon 2, has effectively two methyl groups. The fact that they're the same means you cannot have EZ, and that's exacerbated by the fact that carbon 1 has two hydrogens, again precluding EZ isomers. You only need one carbon to preclude it. Here we got two carbons, so you know. Anyway, a quick way to check is always just to try flipping the right-hand carbon. We look at this is the same. Okay, we flip the right-hand carbon, but we still got two hydrogens there, and so therefore no isomers possible for 2-methyl propene. However, if we go to compound B, and before I do any flipping, look at here at carbon 1, it's got a methyl and a hydrogen. They're different. Look at carbon 2, it's got a methyl, actually carbon 3, it's got a methyl and a hydrogen. They're different. So therefore, because this carbon has different things and this carbon has different things, I'm expecting EZ possibilities. I can confirm that by taking the right-hand carbon and flipping it. So now CH3H on the left-hand one, but now HCH3 flipped on the right-hand one. So we can see that these are different isomers, different molecules, because you can't rotate around a carbon-carbon double bond. As far as the labeling of E and Z, we first of all identify the higher priority group on each carbon, and carbon always beats hydrogen, carbon beats hydrogen. When they're on the same side, it's Z, zusammen, Z, and when they are on opposite sides of the double bond, here this methyl is on top, this is on the bottom, then it's entgegen for E. Pentenoic acid, C4H7COH, has some isomers that can show EZ isomerism, others that cannot. Pent-2-enoic acid can form EZ and give the skeletal formulae for the EZ isomers of this molecule. So first of all, let's draw it out. There's the acid group at carbon 1, carbon 2 is where the double bond starts. Okay. Now, if I just focus on that double bond part, okay, on this carbon down here, I've got the C2H5, an ethyl group, and a hydrogen. On this carbon here, I have a hydrogen and the big acid group. Which one is the higher priority on each? Well, ethyl, carbon always beats hydrogen, carbon always beats hydrogen. Okay, so whether it's E and Z is going to determine where these groups are relative to each other. If I draw it out so they're on opposite sides, so there's the double bond, there's the H's there, there's the acid group on top, the ethyl group on the bottom, they're on opposite sides, so that would be E. And if I draw them on the same side, so again, there's the double bond, here's the ethyl group on top, the acid group on top, then that is the Z isomer. Give the structure of an isomer that cannot show EZ isomerism and explain why it cannot. Well, if you're going to not have EZ isomer, then just one of the carbons, only one has to have it, is the same substituent on each of them. So the easiest way to do this is to just put the double bond as close to the end as possible, the end two carbons. So there we are, it's on the end and it's got two hydrogens there. So therefore it cannot have EZ because it doesn't matter which way you flip it, you've got a hydrogen and a hydrogen. And that will be 1, 2, 3, 4 pentenoic acid. The other possibility is to just, instead of having two hydrogens on the end, have two methyl groups on the end. So there's carbon 1, the acid group, carbon 2, carbon 3, carbon 4 with a methyl on carbon 3. And again, carbon 3 there's got two methyl groups, identical groups, same substituent, can't be EZ. And that would be the 3-methyl I pointed out, 2-buteneoic acid. Buteneoic acid now, because of course you've got one of the carbons is a methyl. So now we want these structures of EZ isomers of 2-bromopent-2-ene. Let's draw out what that is. There's the pent, there's the 2-ene, and there's the 2-bromo. Okay, now when we look at each of these carbons, we see that this carbon, carbon 2, has a bromine and a methyl group on it, and carbon 3 has a hydrogen that's not drawn there and an ethyl group. Now we'll assign priorities. Bromine better than carbon, and carbon better than hydrogen. So now we've just got to draw it so that for one isomer, bromine and the ethyl are on the same side of the double bond, and in the other one they're on opposite sides. So there's the same side, there's the bromine, there's the ethyl group on the same side, and now to draw them on different sides, opposite sides, there's the bromine on the bottom, the ethyl group on the top. When they're on the same, it's Z. When they're on the opposite sides, it's E. Now this is a fun one. The displayed formula of 1,2-dichlorocyclopropane shown below. Draw the displayed formula of another structural isomer of formula C3H4Cl2. Now we look at 3 carbons, and 3 carbons should have 8 hydrogens. This only has 4 plus 2. Chlorine counts as hydrogen for this, or 6. So there is 1 degree of unsaturation. So here we see the 1 degree is reflected as a ring. But you can also have just an extra bond, double bond, to give you that level of unsaturation. So other ring possibilities, here we've got 1,2-dichloro. No reason you can't have both the chlorines on one, so that would be 1,1-dichloropropane. But now let's throw in the alkenes. Got 3 carbons, so the only way you can do it is have carbon 1, carbon 2 being the double bond, and then carbon 3 being all by itself. But now we've got to throw in 2 chlorines onto this. Okay, so we can have both chlorines on the carbon 1, so 1,1-dichloropropene, 1 on carbon 1, 1 on carbon 2, so 1,2-dichloropropene, 1,3-dichloropropene, 2,3-dichloropropene, or 3,3-dichloropropene. Okay, so 5 different double bond structural isomers and 1 extra ring isomer. Now notice it said structural isomers, but I would be remiss if we didn't also mention geometric isomers. First of all, let's look at the double bonded ones. Can you have EZ? Well, this one here you can't. It's 1,1-dichloro, so carbon 1's got 2 chlorines on it. If you got a carbon with the same attached to 2 of the same things, then you can't have the EZ. 1,2-dichloro, on the other hand, you can, because carbon 1's got a chlorine and a hydrogen, carbon 2's got a chlorine and a methyl, so different things. So this can exist in EZ. Okay, 2,3-dichloro, or 2 hydrogens on carbon 1, can't exist like that. 3,3-dichloro, 2 hydrogens on carbon 1, so doesn't exist as EZ. But looking at 1,3-dichloro, you got chlorine and hydrogen, you got hydrogen and a chloromethyl, so that also can exist as EZ. And now looking up here, and this is something that I talk about, it's not in the A-level curricula, at least not the WJEC, but I do mention it, and that is that in the same way that you have these isomers associated with double bonds, because you cannot rotate around a double bond, you also, once you've got a ring, things are fixed as either being above or below the ring. So this one here, there's no doubt you've got a chlorine above, a chlorine below. But over here, you could have a chlorine above and a chlorine below, or another isomer in which both chlorines are above. Okay, and so what we see here is that there's also, although it's not a structural isomer per se, it is a geometric isomer. This would be trans, this would be cis. Last slide, just some quick and dirty questions, some of which are answered in other worksheets, but they're here. So heterolytic bond fission is where you take a bond and you break it so that both electrons from the bond stay on one atom, the more electronegative one. So heterolytic bond means you end up with a cation and an anion. Homolytic bond fission, 1 electron each goes on the atoms when you break the bond, and so what you have here is you effectively have, if we look at it this way, radicals, and you see this, of course, when you talk about the free radical mechanisms that you've discussed. Benzene diazonium ions act as an electrifying reaction. What's the meaning of the term electrophile? Well, phile means liking, electro means loves electrons, which are negative, so loves negatives. And so you'll see this with a species that either has a positively charged atom or one that's electron deficient.